Hi everyone, I'm Abhishek Podal. Welcome back to my channel. Today I've taken a problem from hydraulics unsteady flow chapter. I've taken this numerical from K. Subramania book, which is the very nice book in hydraulics, and so I recommend you to use that book for your study. Okay, so let's get into the problem. Here, a 2300 meter long pipeline is discharging water from a large tank, by using a pipeline having thickness 2.8 mm and the diameter 15 centimeter. And the discharge given here in liter per minute, so that's why you have to convert this discharge into meter cube per second. And the question expects you to determine the water diameter pressure produced due to the valve operation. Here the valve is suddenly closed, so you don't have to check the closing condition, whether it is gradual closure or sudden closure. So that's why it has already stated that sudden closure of valve, so that's why you don't have to check whether it is sudden or gradual. So the question also asks you to draw the pressure time diagram at different points, and that means the valve end and the reservoir end and the middle point and anywhere. That means 575 meter upstream from the valve end. So there are 4 diagrams you have to draw in this question, and this is the most repeated question in hydraulics. This question has already been asked in multiple times and from the book K. Subramania. So I recommended that book already. So here the bulk modulus of water is also given here, 2 into 10 power 9 Newton per meter square, and the modulus of elasticity is equal to 2.08 into 10 power 11 Newton per meter square. Okay, so now let's write the given parameters over here. So the given parameter are the length of the pipeline. Let's write the length of the pipeline here, that is 2300 meter. And the diameter of the pipeline is how much? D is equal to 0.15 meter. And the thickness of the pipeline is, we can say this is the TM. TM is how much? The TM is 2.8 into 10 to the power minus 3 meter. And the discharge is given here in discharge liters per minute. So you have to convert that 2200 liter into 10 to the power minus 3 meter cube per minute, means that is, you can divide it by 60. So that's why you are going to get the discharge 0.0367 meter cube per second is the discharge. So we have to convert this into meter cube per second. So now let's get the velocity of the flow inside the pipeline before the valve closing condition. That is, velocity of flow is V is equal to you can do like Q by area. So here you can write like 4Q by pi d square, and that is the area of the cross section of the pipeline. Okay, so if you do this, so you are going to get, if you put the value of discharge here, if you put the value of diameter here, you are going to get the 4 into Q is 0.0367 divided by pi into diameter, how much? The diameter is 0.15 square. That is going to be 2.077 meter per second. That is going to be 2.077 meter per second. Okay, so you have got the velocity of the flow inside the pipeline before the valve closing condition. And you have got the velocity, and you are going to find out now the celerity, that is the velocity of pressure wave. Okay, so velocity of pressure wave is denoted as C, so which is also called celerity or celerity. You can write like this as a celerity. So celerity is we have got a formula. The celerity formula is how much? K by rho 1 plus dk by ETM inside on the square root. Okay, so put it inside the square root, and you have already given here the value of KNE. K bulk modulus value is given already for water, and the still modulus velocity of steel, that is 2.08 into 10 power 11 Pascal. Okay, so you don't have to convert, it is already given in Newton per meter square Pascal, so we don't have to convert. So otherwise you have to convert it into Newton per meter square. So if you put all this value over here, how much you get? Let's write the value of K, that is 2 into 10 to the power 9 divided rho is how much? In most of the case the water is flowing inside the pipeline in the unsteady flow chapter. So 1 plus diameter is how much? 0.15. K is how much? K is gonna be 2 into 10 power 9, and ETM is how much? E is equal to 2.08 into 10 to the power 11. Tm is how much? Tm is equal to, Tm is 2.8 into 10 to the power minus 3 inside the square root. So that's why you have to put it inside the square root. So if you put it inside the square root, you are going to get how much? The celerity is going to be 1148.93. You are going to get this much. 1148.93, you are going to get this much, and this is in terms of in meter per second. Okay, so you have to write it in meter per second. So that's why it is written like meter per second, which is also the velocity, but this is the velocity of the pressure wave. It is always greater than the velocity of sound, which is 332 meter per second. So you have got the celerity, and now let's go to find out the water hammer pressure generated due to the valve operation. Here the valve is suddenly closed. The valve is suddenly closed here, and for the sudden closure of valve, in pipe elastic, how do you know pipe elastic here? Pipe is elastic because the modulus of elasticity given here. So in this case, bulk modulus of water both and the modulus of elasticity E both are given. So that's why it is under the sudden closure of valve and pipe elastic topic. Okay, so you can use this celerity formula. So because this lies under the sudden closure of valve and pipe is elastic case. So if this was the sudden closure of valve, pipe is rigid, what would you do? If this case was the sudden closure of valve, pipe is rigid, you do that this one. The formula is this one. Okay, because in that case the modulus of elasticity is going to be infinity. If the pipe is rigid, if the pipe was rigid, what would you do? So you do like this. This is the formula for the celerity, which is only the K by rho. Okay, but this is not the case. This is the case of sudden closure of valve and pipe is elastic. So we are doing this. We are using this formula. Okay, you understand? So now let's go to the another part, that is let's go to find out the water hammer pressure. I have already told you I have already got the celerity C. So now let's go to find out the water hammer pressure generated due to the valve operation. Okay, so that is pH is equal to rho Vc. The formula is pH is equal to rho Vc. You have already got the velocity, and rho is 1000 in case of water, and velocity is how much? The velocity is going to be 2.077 into celerity is how much? 1148.93 meter per second. So if you do this, and you are going to get let's calculate this in the calculator. 1000 into 2.077 into 1148.93 is going to be 2386.33. You can do like this, 2686.33 kilopascal. Okay, kilopascal, but you get in the pascal. That pascal is how much? 2386327.661. This is going to be pascal, Newton per meter square. Okay, so if you divide it by 1000, you are going to get 2386.33 kilopascal. Okay, or kilonewton per meter square. Newton per meter square. We are going to do it in kilopascal. So let's we have found out the water hammer pressure generated. Okay, so let's go to this. Let's go to this case, the pressure time diagram. In this case, let's sketch the pressure time diagram. In the first case, you have to sketch the pressure time diagram at the valve end. Okay, so let's draw the valve first of all. So okay, let's denote this as a valve. So valve is V here. So the valve end is V, and the reservoir end is, let's say this is N, and the middle point is, let's say this is M, and anywhere that is, let's say P. So you can say the point P. Okay. So the question asks you in the 4 cases here the valve end, the pressure time diagram at the valve end. So if you close the valve, the celerity will be generated in this direction. Okay, first in this direction it goes here, and it will act like it goes here to the reservoir, and it also again comes back and again goes and again back. So this is how the celerity would be, and the velocity of flow of water is initially in this direction B. Okay, So now let's draw the pressure time diagram in case of let's say the pressure time diagram, pressure in the y-axis and the time in the x-axis. It means that you are putting the pressure meter over here to check whether the pressure, how much pressure is occurring after the valve closure conditions. Okay, so understand that you are putting the pressure meter over here in this valve. So that's why pressure time diagram at the valve end, pressure time diagram at the valve end, valve end is how much? B. Valve end, which one is the valve end? B. Okay, so now let's draw the pressure time diagram like this. So while drawing this, we need the we have to put the water hammer pressure in this in y-axis. So in x-axis we are going to put the time. So while drawing the pressure time diagram, the fluctuation is drawn. So pH plus positive pressure is in upward and negative pressure is downward. pH minus pH plus. This is how you draw this. Okay. So now, first of all, the diagram is like this. Equal block. Draw the equal block here. So we are only concerned with the maximum pressure generated initially. So later on it will go damping. So that's why we don't have to consider that damping case. So first of all, the pressure is how much? The positive pressure, that is 2386.33 kilopascal plus. You have to do like plus here. So this is kilopascal, and this is going to be like negative pressure in this part, minus 2386.33 kilopascal. This is the negative pressure, and we only have to consider the highest pressure generated due to the valve closure condition, because we don't have to consider the damping cases. Later on the pressure will be damped and the pressure will be taken up by the water as well as the pipe. So that's why we only have to consider the first case. The first case is the maximum pressure generated, and the maximum pressure generated is the 2386 kilopascal, which we have calculated this much. So that's why how much is this one? This one is going to be like one cycle, that is 2L by C. And this another one is 2L by C. So this is 2L by C and 2L by C. Okay. So this is how you draw this. And if you put the value of 2L by C, we are going to get let's calculate 2L by C. How much? 2 into L is how much? We have got L is 2300 meter. And C is how much? C is 1148.93. That is going to be like 4 seconds. So 4.0037. That is, I've taken this as a 4 second. Okay. This is a one complete cycle. You can say 4 second, 4 second, and 4 second. So this is the diagram of in the case when the pressure meter is placed in the valve end. So you are first how the diagram is drawn. When the wave passes this valve, it will feel the pressure all the time. When the valve is closed, the wave generated first travels towards the reservoir. So that's why it has just crossed the valve end all the time. So the reservoir is too much large, and then the wave just goes at this point N and comes back. The oscillation occurs until the damping occurs. Okay, so oscillation takes place until the damping occurs. So that's why first of all, when the wave travel this distance L, so this distance L, the time taken from traveling from this valve to the reservoir end is how much? L, distance traveled by velocity L by C. Okay. So L by C. First, the wave takes time L by C to travel from this valve to the reservoir end N. So after that, the wave returns back and goes to this point valve again. So how much is the distance, total distance that is? That is going to be L by C first. Distance traveled from this valve to reservoir end, that is L by C. And again from reservoir end to valve, that is going to be L by C. So if you put this both, if you add this both, you are going to get 2L by C. That is the time, one complete cycle. And this is going to be positive. Here the elastic compression is occurring, and after this the elastic tension is occurring. So that's why this is positive negative is happening here. So here there is no zero pressure anywhere. At this point you can see here, at this point just left the positive pressure, that is 2386.33 kilopascal, and just right at this point the negative pressure, that is 2386.33 kilopascal. So there is no zero pressure point. So that's why you can say that in the valve end all the time the pressure is occurring all the time. You can see the pressure in the pressure meter, but there is a fluctuation of the pressure, sometimes positive pressure, sometimes negative pressure. So that's why after the 8 second of closure, 4 second plus 4 second 8 second, you have to say that after the 8 second of closure the pressure is how much? Just left negative pressure, just right positive pressure. You have to say like that. So after 4 second of closure, how much is the pressure? 8 second of closure, 8 second of closure, the pressure is how much? The pressure is gonna be whatever pressure P left. How much is pressure P left? That is the pressure at the left is minus 2386.33 kilopascal, and the pressure at the right is plus 2386.33 kilopascal. You have to say like that. Okay, so after 4 second, after 8 second, the pressure is how much? Just left negative and just right positive. So after let's say after 6 second, 4 plus 2 6 second, it is here. After 6 second, the pressure is how much? The negative pressure, that is after the 6 second, the pressure is how much? This is negative pressure, minus 2386.33 kilopascal. So this is how the question asks you in the examination. So after how much time the pressure is how much? So this is how the question asks you. So now let's go to draw the pressure time diagram at the reservoir end. Okay, so let's draw the pressure time diagram at the reservoir end. The conclusion is that after when a valve is closed, and when the valve is closed, the pressure at the valve is all the time there is pressure happening. Okay, if you put the pressure meter there, you see the pressure positive negative all the time. So there is a fluctuation in the pressure. So that's why this is called the unsteady flow in the pipeline. Okay, now let's draw the pressure time diagram at the reservoir end. The second part. Pressure time diagram at the reservoir end. So you can draw reservoir over here, and the reservoir, I have already told you that when the wave crosses the point feels pressure all the time. Remember, when the wave crosses the point, the pressure feels all the time. That pressure might be positive pressure, or that pressure might be negative pressure. Okay, now we are going to draw the pressure time diagram at the reservoir end N. Okay, so for that let's put pressure in the y-axis and time in the x-axis. Okay, so pressure, this is positive pressure PH plus and the negative pressure PH minus. Okay, so now let's draw this. First of all, the wave takes time L by C to reach the point this N. The valve pressure is generated at this point B, and it takes time distance traveled by velocity, that is L by C time to reach this point. When it reaches this point, after this only it feels the pressure. So that's why before reaching N there is no pressure. So you can write like this is L by C. You can write like this is L by C. First of all, at the point time L by C, there is no pressure. Pressure 0 here. Pressure is 0 here. Pressure 0. Okay, there is no pressure. So when it reaches this point reservoir end, there is just a pressure generated, just a vertical line here. The pressure is how much? The pressure is positive pressure, that is 2386.33 kilopascal. Okay, so and wait, after this it cannot just go from this large reservoir up. You cannot really release like a sauce tank, So that's why the pressure returns back. The wave returns back, goes to this point, taking the time L by C, and again return back to this point, taking another time L by C. If you add up, then you are going to get the 2L by C. Okay, so how much is this one? 2L by C. After this 2L by C, there is up to this point 2L by C, there is another negative pressure. Okay, negative pressure. You cannot draw this as a upward. You cannot draw this. Okay, so in this point the first elastic compression is occurring, and after this the elastic tension is occurring. So at this point you can say like there is a pressure of minus 2386.33 kilopascal. Okay, so this is how you have to draw. So after this again the positive pressure comes, a vertical line only. So that is after this 2L by C time, the pressure is going to be again the plus 2386 kilopascal. This is how you remember that first L by C there is no pressure, and there is only the vertical line here, because it just touches this point and this leaves this point, so it does not crosses this point. So that you can say that it feels the pressure all the time when it crosses. So in this case just touches. So wave first just toss this one and a vertical line, it leaves, and there is no pressure in this zone. There is a pressure 0 in this zone. Pressure 0 in this zone. So that's why there is a pressure 0 in this zone and the pressure 0 in this zone. Pressure 0. Because why? Because the wave does not crosses the point. So if it crosses the point all the time, the pressure it feels the pressure. So here you can see here the bulb, here in this point bulb, there is all the pressure all the time. There is a positive pressure until the first cycle and negative pressure another cycle. Positive pressure is the elastic compression and negative pressure is the elastic tension. So elastic compression tension occurring all the time, and at last the damping will occur. I hope you understand this. And now remember that first L by C time there is no pressure, and it just reaches this after time L by C, it reaches the reservoir end. That's why there is only a positive pressure. And after this it releases, so there is no pressure. Again it makes a negative pressure over here, and just it releases. Just the wave just does not crosses this point. It goes back. So that's why this is how you draw the pressure time diagram at the reservoir end. Okay. So now let's go to draw the pressure time diagram at the middle point. Okay. So how do you draw the pressure time diagram at the middle point? So pressure time diagram at middle point. Diagram at middle point. The concept is same, like I've drawn the diagram before. The concept is same like that, but it's better to remember in the examination. So that's why I'm going to draw this one is time in the x-axis here, time, and the pressure, positive pressure upward and negative pressure downward. So in this case we are only considering the water hammer pressure, we are not considering the static pressure. So that's why okay, first it's better to remember, I've already told you L L by 2C, and up to L by 2C there is no pressure, zero pressure, and after L by 2C there is a L by 2C, L by C, up to the time L by C there is positive pressure, and again for the time L by 2C there is no pressure at all. So one cycle is completed. If you add all this, so you have to draw this figure like this. This is the reservoir, and this is a L. You are going to draw the pressure time diagram at this middle point, right? So the valve is still in the valve end. This one valve, I am not changing the valve, I am just changing the point. So that's why this is at the point, middle point. So at the middle point, it is supposed that you are putting the pressure meter at the middle point. It actually like putting the pressure meter at the middle point and looking at the pressure meter all the time. So because the time is passing here and you are looking at the pressure meter and you are just plotting this diagram. This is the concept is that. So this is the first cycle. If you add up this 1 by 2C, 1 by L by 2C, L by C and L by 2C, you are going to get one cycle that is a complete one positive cycle, and that positive cycle is called elastic compression. In this point there is a positive pressure and going to be the maximum pressure. We are not considering the damped pressure. This is the first pressure experienced by the valve closure condition, that is positive kilopascal. So if you this is the first cycle. After this cycle you just copy paste this one. So this one is going to be L by C, L by 2C. The same you are going to draw at the draw below. Okay, so this is going to be like L by 2C, L by C, and L by 2C, L by 2C. Okay, so okay, let's put the value here. Let's put the value over here. L is how much? 2300 meter. Divided by 2C, 2 into C is 1148.39. You're going to get like 1 second. Okay, L by 2C is 1 second, and L by C is how much? 2300, and C is how much? 1148.93. That is going to be 2 second. 2 second. This is going to be 1 second, and this is also 1 second, and 2 second, and 1 second. You draw like this. Okay, so this is how you draw, and this is the one elastic compression, and this is another cycle that is a elastic tension. So when the first cycle completes, put a bullet mark over here. Okay, so now I have drawn this one also, and I also have to put the value over here. L by C, how much is the value? L by C L is 2300 meter in the case of pressure time diagram at the reservoir end. Okay, let's put the value over here. 2300 1148.39. That is going to be like 2 second. This is going to be 2 second, and this is going to be 4 second. Okay, and this is going to be again 4 second. So this is how you plot it, and you write the value over here by substituting the length and the celerity. So okay, we have completed this pressure time diagram at the middle point. So now let's go to draw the pressure time diagram at the anywhere. That is, anywhere means where. The question asks you to draw the pressure time diagram 575 meter upstream from the pressure time diagram